Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 9th, 2025, just yesterday. It introduces a new framework that boosts the math reasoning accuracy of a general-purpose LLM, like QN 2.532b, by over 3%. The paper is titled, First Return, Entropy-Eliciting Explore, and its method for improving training stability is quite clever. The authors address a key challenge in reinforcement learning, where models often struggle to explore different solutions effectively. Alright, so how does this new framework, called First Return Entropy-Eliciting Explore, actually work? This first figure gives us a great overview of its two-stage process. In stage 1, First Return, the model generates a solution path. Then, it calculates the entropy, which is a measure of the model's uncertainty at each step, and uses the most uncertain points to break the solution into smaller chunks. Next, in stage 2, Entropy-Eliciting Explore, the model tries out many different continuations from those uncertain points, rewarding the successful ones to guide its learning. Building on that idea of using entropy, this next figure shows us which words, or tokens, tend to have the highest uncertainty. It's a word cloud, and we see words like suppose, since, maybe, and consider. These are exactly the kinds of words you'd use when making a logical jump or starting a new step in a proof. This insight is really the key here. It confirms that the model is most uncertain at these critical reasoning junctions, which validates the whole approach of using these points to guide exploration. So these plots really drive that point home, showing how this new framework helps maintain exploration during training. We're looking at a comparison with a baseline method called Group Relative Policy Optimization, or GRPO++. The chart tracks entropy loss, which is a measure of how much the model's uncertainty is being reduced. You can see the baseline method, in blue, suffers from what's called entropy collapse. Its exploration drops to almost zero very quickly. In contrast, the new method, in red, maintains and even increases its entropy, showing it continues to explore different solutions. Moving to the results. This table really shows the payoff of all that sustained exploration. It compares the new First Return Entropy-Eliciting Explore method against the baseline Group Relative Policy Optimization++ on several math benchmarks. We see consistent improvements, especially for the general-purpose models. For example, the larger QN 2.532b model jumps from 62.5% to 65.6% average accuracy. That's over a 3% boost. The gains are a bit smaller for the math-specialized model, but the trend is clear. This method works. And these charts really dig into why the model is getting better. They show the number of what are called all-right trajectories. A trajectory is just a solution path. And an all-right one means that every single exploratory attempt the model made from a key reasoning step turned out to be correct. You can see the new First Return Entropy-Eliciting Explore method, in red, generates far more of these highly reliable solution paths than the baseline. This shows it's learning to build more consistently correct lines of reasoning. So, to wrap things up, what we're really seeing is a clever solution to a tough problem. The key insight of First Return Entropy-Eliciting Explore is using the model's own uncertainty, its entropy, to guide exploration. This avoids the common issue, where models stop exploring too early. Instead, it helps them build more reliable and correct reasoning paths, or trajectories. This whole approach is a form of reinforcement learning from verifiable rewards, a technique where models learn from getting a final, verifiable answer. Thanks for joining the AI Research Roundup. I'm Alex.